this is Miss Beatenbow, and we're going to go over proving and using similarity in our polygons. Here you'll notice that they're telling us similar figures, and we use this little swerved line to represent triangle ABC being similar to triangle DEF. And we're going to go over how we can prove that and what we can do once we know two polygons are similar. So what exactly are similar figures? Similar figures are figures that all of the corresponding angles are congruent, so all of the corresponding angles have the exact same measure, and all of the sides are proportional. Here you'll notice that we have these arches with slashes through them. The one slash would represent that it is congruent to this angle over here. The 2 slash angles would be congruent, and the 3 slash angles would be congruent. So without knowing the exact measures, we do know that all of these angles are congruent. You will also note here that even though these shapes are similar, the orientation has changed. So when doing your problems and you're finding those corresponding angles and corresponding sides, it's very important to make sure that you are doing it based on which ones correspond to one another and not just which are in the same location. So if we know that the sides are supposed to be proportional, what does that mean? Well, we are given two triangles here and we're asked, are these similar? We are told they're rectangles, and so by the definition of a rectangle, we know that these are all 90-degree angles, and because all the angles are the same, we would be able to say yes, they are. But let's look at how to tell using the sides, are these similar or not? I like to always list out which sides correspond to the other. So here I know my short side, CD, is going to correspond to the short side of my other rectangle, GH. And my longer length, AD, is going to correspond to EH. So I can set up my proportions as fractions to determine, are they the same? And I'm going to do CD, which is 5, over GH, which is 3. And I need to see, is that equal? Is it the same proportion as AD to EH? AD is 25 over EH, which is 15. Well, 25 and 15 are both divisible by 5. 25 divided by 5 will give me 5, and 15 divided by 5 will give me 3. So I know that once simplified, they do have the same proportion. Since they have the same proportion, all of my corresponding sides must, because we know the same will be true for BC to FG and BA to FE, since they will have the same measures as well. And I can say, yes, they are, due to the corresponding sides all having the same proportion. I can also, if I know two figures are similar, use those proportions to help me find the missing length. So here we're given two triangles. It's important to note that the problem does tell us they are similar. If we don't know they're similar, then we wouldn't be able to do this. And we need to find the missing length. Here you'll notice that the triangles are in the same orientation. And I'm going to set up my proportion as the small side over the big side for each corresponding side. So I'm going to use 6 and 18, these two corresponding sides. I know I need to find the missing length, which would be the question mark. So I have to use the corresponding side that goes with that. So for the two sides I know, the small length is 6. My big length for the larger one is going to be 18. For the small figure, I don't know, so I'm going to go ahead and use a variable, use x. And I do know the length of the bigger triangle, which is 21. Now I have a fraction equal to a fraction. Here I can go ahead and cross multiply this through. So I'm going to do 6 times 21. That gives me 126. Multiplying across the other diagonal, 18 times x gives me 18x. Now I have a nice simple one-step equation. I can solve, divide both sides by 18. 126 divided by 18 will give me 7. So I know 7 equals x. Looking at this problem, you can also notice if I start going from my small to the big one, that there is a ratio between all the sides. 6 times 3 gives me 18. 8 times 3 gives me 24. So to follow that same process, 7, which we now know, times 3 gives me 21. So sometimes you can identify the ratios, but if you can't, setting up the proportions equal to one another, cross multiplying and solving will always help you get that missing dimension on your similar figures. So now we've seen how we can prove similarity of our polygons and how we can use similarity to find missing links on our polygons. However, with triangles, there's some really specific things that we can do and ways that we can prove similarity. One of them being the angle-angle similarity postulate. And that tells us if 2 or all 3 of the triangle's angles are congruent, then the triangles must be similar. So I need to look at my triangles and see, well, do I have 2 angles that are the exact same measure that correspond? Well, here I'm given 48. Here I don't have anything. For angle C, I have nothing, but angle F, I have 42, and then I'm given these little boxes which represent right angles. So there's a couple things we need to make sure we remember about our triangles. One of those being that every triangle has a total of 180 degrees as the sum of the angles. So if we're given 2 angles, we can help solve for the third angle. The other thing being that a right angle is 90 degrees. So for this little triangle, I don't know what C is, but I know that 180 must equal 48 plus 90 for my right angle, plus whatever C is. I don't know, so I'm going to go ahead and use a variable. I can go ahead and solve this for x. 48 plus 90 is going to give me 138. 180 equals 138 plus x now. I can subtract 138 from both sides, and that will give me that 42 is my x value. So I know angle C is going to be 42 degrees. Now I know that angles B and E have the same measure because they're both right angles 90 degrees, and I know C and F have the same measure. So using the angle-angle similarity postulate, I can say that these 2 triangles are similar since they have 2 congruent corresponding angles. Another way we can prove similarity in triangles is the side angle side similarity postulate. And that's going to tell us that if we have 2 triangles with the sides that are attached to the corresponding angle that is congruent, that we can show those proportions being the same of the corresponding sides, and therefore the triangles must be similar. Well, here I can look at angle A and angle X. They both are obviously 63 degrees, so we know we have corresponding congruent angles. So now we need to check the sides. We have AC to XZ. If I do my sides, the small 2 over the big 4. And I need to see, is that proportional? Is it this equal to AB to XC? AB being 2.5. XZ being 5. 2 and 4 are both divisible by 2, so 2 over 2 gives me 1. 4 divided by 2 gives me 2. If I'm not sure, I could plug the 2.5 and the 5 into the calculator and see what decimal that simplifies to, but I also know 2.5 goes into itself 1 time and goes into 5 2 times. These are the same proportions, so I have a side with a corresponding angle in between that is proportional to the other attached side. So by side angle side, I can prove that these two triangles are similar. And the last postulate of triangles is based off of what we were talking about earlier with similar figures, of that they have the same corresponding angles and all of the corresponding sides are going to be proportional. And using the side similarity postulate, that's what we're focusing on, that 3 corresponding proportional sides are shared amongst the 2 triangles. And so I have to check all 3 sides because that's all I'm given in these. I can't use anything with angles since nothing is given. Even if they look the same, looks we can't prove congruency, so we have to use our sides here. And I can double check and make sure I have the right corresponding sides. 2 is the smallest on my little one, 8 is the smallest on my larger one, so I know those 2 must be the corresponding. So 2 over 8. Then I go to my middle lengths, 12 and 3. Again, I'm still going to do, and my preference is to do this smaller on top most of the time. I could do 12 over 3 as well, as long as it's the same. If you do small on top, you have to do small on top for each proportion. If you do big on top, you would have to do big on top for each. And my largest lengths, 16 and 4, which will give me 4 over 16. Again, I have to simplify each of them, or I could go ahead and plug these all in my calculator and figure out what decimal is 2 over 8. But 2 and 8 are both divisible by 2, giving me 1 over 4. 3 and 12 are both divisible by 3, giving me, again, 1 over 4, so this is looking good. And 4 and 16 are both divisible by 4, giving me 1 over 4. All 3 of these are the same, so I can say, using the side similarity postulate, since they all have the same proportion, these 2 are similar triangles. If any one of those proportions came out different than 1 over 4, we would not have them all having the same proportion, so it would not be. So you do need to check all 3 sides whenever checking to use the side similarity postulate. So we have gone over all of these great objectives from your lesson. Please go ahead and, if you have further questions, use the tutoring or reach out to your teacher for some extra explanation. I hope this helped.